Hi there guys, this is 12G and we're going to extend our phase portraits, which we did in 12F, to now include eigenvalues which could be complex. So just to recap on 12F first, before we got to phase portraits, so we came up with this solution. This was our solution to a system of coupled differential equations. And so the solution is here. We're using eigenvalues and eigenvectors. And those are coming from the setup of our derivatives of x and y with respect to t in terms of a matrix times by xy. So, for example, I know we could have x dot y dot, that would represent x dot as a vector. And we could potentially say that that's equal to a matrix, maybe let's say 2, 1, 0, 3, as applied to x, y, and then we could actually multiply this out. We could work it out, and we could do that would give us 2x plus y in a vector now. Again, we're looking for a vector answer here. Okay. And then when we times these across, we're going to get 3y there. So, that would give us dy dt, for example, is equal to 3y, and dt would be equal to this. So where we're dependent on both x and y. Okay, so that's what we dealt with last time round. We then moved into phase portraits, but last time round we always found eigenvectors, which were real values. Now we're considering the cases where, with what happens when they're not real values, when they're complex. Okay, so let's have a little look at what the book is doing in terms of the exercise. So you can see there's a little start bit down here on page 553, so just a bit of an introduction here. And in that introduction, they also say a reminder. Next page. They also say that you always get your complex solutions to quadratics coming in pairs. And we've discussed that one before. You can look at the structure of the quadratic formula to show that they're always coming in a version of a plus and a minus the square root of the discriminant. So that's where you're getting your plus 3i in this case and minus 3i. So you're always going to get solutions in these pairs. Okay, so that's kind of important. But in terms of the exercise here, so 12G is here, there's actually no example beforehand. You really have to go through some of the investigation, or potentially, if you're feeling brave, if you're feeling particularly confident with this stuff, you can go into looking at this key box here, and you can try and make some sense of that. And that's what we're going to build up to, of course, throughout the exercise. Now, let's just go through that and show what we're working towards. And they're saying here that if we're getting these complex eigenvalues, that's new to this exercise, of course, then the trajectories of our phase portraits will form circles or ellipses if A is equal to 0. In other words, if you've only got an imaginary part, you don't have a real part to the complex number as well. Okay, so in other words, you'll get circles just going round one direction or the other direction. Okay, and there'll be concentric circles or potentially concentric ellipses, and those ellipses can be like this. Okay, so they don't necessarily need to be kind of square on, if you like. So again, they could go one direction or they could go in the other direction as well. And in fact, the direction is fairly easy to find out. In fact, there's a point here which turns out is really quite straightforward, as you'll see through the investigation. But essentially, have a look at a point that you're choosing on this trajectory, and you can see what's happening with dy dt, dx dt, in this case, dx dt, to see if we're increasing in this direction or increasing in this direction, to see which way around we're going around these phase portraits. Okay, so that's what's happening when A is equal to 0. And then we'll also show through this investigation just a little extension. And I'm not going to do the entire investigation, but there's just a little extension where I can show you that essentially wherever you start, you might spiral outwards if A is greater than 0, and you might spiral inwards towards the, it's not very good, spiral inwards towards the origin here. Okay, so it's spiraling towards the origin if A is less than 0. And again, that's a little extension from the investigation once we've done the first part. So I'm not going to do all of the investigation, I will do some of it, but this is essentially what you need to know. But let's have a look at making some sense of this through the investigation now. Okay, so there we go. You can see some of our diagrams here. Okay, so investigation 6, it says to start off with, let's take A and B, 1A and B here. And here we go. And it says find the eigenvalues for the following system of equations. And we've got x dot and we've got y dot in a similar way to the case of real eigenvalues. And we've got this general solution here. So we're going to go with the general solution which we've got from before as well. Okay, so let's set this one up. Remember, of course, we have x dot as a matrix, as a vector, equal to the matrix times by x, and x is your xy vector, of course. And so we're trying to find the solutions of this, and we're using eigenvalues and eigenvectors to sort this one out. Okay, so we're going to find the solutions first of all for the eigenvalues, that is. So the matrix in this case is going to be x dot. You can see that we've got here 0 and 2 and -2 and 0 there. That's our matrix, which is applying to xy being this thing here. Okay, now obviously if you times this by this, you'll see that you get for x dot, you'll get 2y, and that's exactly what we're getting out here, and so on. Okay, so this is the matrix which we've got. Now remember, of course, as well, that if we're trying to look for our eigenvectors, eigenvalues, sorry, we're going to need to do the matrix, take away lambda, lots of the identity matrix, multiplied by x, and is equal to 0. So that's just taking this algebraically a little bit further. And of course, we're dealing with things in 2 dimensions. So finding the eigenvalues, then we basically need to find this matrix first. Of course, that matrix is, so this one here is going to give us the matrix minus lambda, 2, and -2, and minus lambda. Now that's the matrix, but we need to find when the determinant is equal to 0. And when that's equal to 0, that's these two things times together to take away these two things. So we're getting lambda squared and plus 4 there. So you can now see we're going to get complex solutions to this. So we're going to get lambda is equal to the square root of -4. Okay, so that's going to give us, that's plus or minus, of course, plus or minus, and then we've got square root of 4 is 2, and the square root of -1 is I. Okay, so now we've got lambda 1 is equal to 2I, and lambda 2 is equal to -2I. Of course, you could swap them around, but I'm just matching up with the way in which the book has delivered it here. So this bit here, saying a e to the b I t times by v1, v1 here being the eigenvector which is associated with this eigenvalue, and I've made this one positive, and then this one is negative. So this one says minus bit. So for us, when it says state the value of b is just 2 here. So we'll change this into a e to the 2it multiplied by the eigenvector. Okay, now there's a bit of an issue in the next one, although I want to try and take this further to give you a concrete example. But just to show you that in the book, it's saying A and B and the elements of the two eigenvectors can be complex numbers. But values can be found in which both x and y are real for values of t. This is beyond the course. So they are not asking us here to work out the eigenvectors in these systems. And if you have a look at the questions, they're in fact just talking about the phase portraits. But I'm going to try and give you a concrete example here. And I think part of the reason why they've stopped at that is because there's a bit of an issue with the eigenvectors now. So if we take this further, and so I'm going to make a concrete example of this. I'm going to write it in this form. I'm going to come up with a value of a and b and some eigenvectors. And I'm going to show you essentially that by replacing this with this form here, so this is obviously Euler's form for our complex numbers. If we replace it by this, we're going to show that the function is periodic, and the fact that it's periodic will mean to say that it will be coming back round in a circle or a spiral or whatever. Okay, so we're going to take this a little bit further, but you'll see there's a bit of an issue here. So if I put in lambda 1 back into here, and so to work out the eigenvectors, we now can say we've got minus 2i, 2, and then minus 2, and then minus 2i here. We're multiplying that by x, y, and we're getting out the answer 0, 0. Okay, so when we multiply this by this to get out a 0, we're obviously getting minus 2i x plus 2y is equal to 0. Now, cancel the 2 out there. And if we take the xi to the other side, we get y equals ix. And that's going to give us the eigenvector 1 for x we could choose. And then 1 times I would give us out y. So that would be I there. Now, here's the slight issue in that when you do this times this, get this. To get the first equation there, you're going to get this eigenvector. But when you do this times this, get this, you end up getting 1 and minus I there. Now, I don't have an answer for why those things are different, but I think that you can work with either. I think it will work. And I think that's why the book says that A, B, and the elements of the two eigenvalues can be complex numbers, but values can be found. So there's kind of an ambiguous statement there. They're not saying that they are particular numbers, but there are numbers that can be found to make this work. So yeah, so I'm going to continue essentially with this eigenvector. And then if you do the same thing when you put this in, you get again a choice of eigenvectors. The eigenvectors are 1 and minus I, and 1 and I. So again, I'm going to go with the 1 and the minus I there. So I'm going with eigenvectors which can be found. Okay, so I'm kind of fudging this a little bit because I know that this example will work. Okay, and I'm also going to go with some initial conditions, which I know work as well, which are that when x is 2 and y is 0, t is equal to 0, and that also means that a is 1 and b is 1 as well. Now, I found an example which works there. There is not a question which is taking this further, but I want to show you a concrete example of what they're coming up with next when they're putting it in this form here. Okay, so putting all of that together, okay, just get rid of everything here on this page at the moment. So putting all of that together, we're going to get out xy is equal to, now we're going to have a is equal to 1, b is equal to 1. So just write this down. When a is 1, b is 1, t is 0, and x is 2, and y is 0. Now, I'm kind of doing this back to front because actually I put in a is 1 and b is 1 and t is 0, and I worked out these two things here, which you'll see in a second. Whereas normally we get given these initial conditions and we work out what a and b are for a particular solution. I'm doing this a bit back to front. So we've got xy is equal to, and I'm going to say e, and then this bit here is going to give us b. So for us, b was 2i, t, and our eigenvector was 1i, and then plus, and I'm going with b is 1, e to the minus 2i, so that was the other eigenvector in this example here, so we're still doing that example. And then with the other eigenvector put the t on the end, and the other eigenvector was 1 and minus I. Okay, so now we're going to switch the polar forms here. We're going to replace the E2IT with the cis theta form, so from Euler's form to the other polar form. And we can write this now as xy is equal to cos 2t plus I sine 2t multiplied by 1i, that vector, and then plus, and then we've got cos minus 2t, one in brackets, plus I sine minus 2t, and that's multiplied by 1 and minus I. Okay, so now we can think of values of t to find our positions. And so first of all, we're going to show this is our initial condition when t is equal to 0, with a is 1 and b is 1. Okay, now let's put in t is equal to 0 in here. Of course, cos of 0 is 1. Sine of 0 is 0, so that's going to disappear. This is going to disappear as well. And cos of 0 again is 1. So we're going to get 1 lot of this plus 1 lot of this. So we're getting out the coordinate point x, y equals, and we'll get 1 and I added together to 1 and minus I. You can see that's 2, 0. So that gives us the condition here as well. So that's the initial conditions verified. So I'm kind of lucky that A and B worked kind of nicely there. That's my original choice. Now, because we've got cos, we're thinking let's put in values of theta here, and because this one is going to be 2t, then the frequency of this, or our period if you like, is going to be 2 pi over 2. It's 2 pi over b. B in our case is the 2. So that's going to give us pi. So the period of this is going to be pi. We know that, right? So, cos of 2t is going to have 2 repetitions in 360 degrees, or 2 pi radians. So it's going to repeat once between 0 and pi. So that's our period. Okay, so what I'm going to do is choose some clever values here, and I'm going to choose to split up pi, because I know we'll get a repetition. We'll be back to where we started again, pi in this case. So I'm going to choose some other values in the center. I'll choose pi over 2, choose pi over 4, I'll choose 3 pi over 4 there as well. It's just quarter, a half, 3/4, and a whole. So those are the values which I'm going to choose, and I can see, of course, that I'm going to get back to the start again when I put in pi, because I'll get the same values out again when I put in pi for t. I'll get cos of 2 pi, and cos of 2 pi will again give me 1. Okay, so let's go with t is equal to pi over 4, and then xy is going to be equal to, again, pi over 4. That's 90 degrees, but when let's just think, pi over 4, sorry, is 45 degrees. And with cos, the same on both sides. Okay, so when we double 45 degrees, we get 90 degrees. Cos of 90 is 0. Okay, so we're going to have 0 here and 0 here. We've got the same on both sides. And a little sketch of the sine graph here. So the sine graph is going to go like this. And when we put in sine of 90, when we put pi over 4 in here, that becomes 90 degrees, essentially pi over 2. And sine of pi over 2 is 1, so that's going to give us 1. And this one is going to give us minus 1, because this is an odd function. Okay, so we'll get minus 1 out of that, and of course this will disappear again. Okay, right, so this is going to give us 1i minus 1 minus I, And here we're going to get 1 take away 1 is 0. And then we're going to get, I'm missing something here. I'm missing the fact that I need to times those by I again as well. So there's my I. And just put that I in there, try and squeeze that one in. Okay, so the top is going to clearly cancel. And on the bottom, we get I multiplied by I, which is minus 1, minus minus I. So that's going to give us 2 lots of minus 1, which is minus 2 there. Okay, and similarly, you can continue doing this for pi over 2 and 3 pi over 4. And you're going to get your solutions minus 2, 0, and you'll get your solution down here of 0 and 2. Okay, so now we're in a position where we can plot all of these points. So let's plot these points. Let's just come up with a quick graph over here. And so you can see when t is 0, you get out 2. When, so 2, 0 there. When t is pi over 4, that's 0 and minus 2, so that's down here. So this is the vector, position vector, if you like. This is x at 0, and this would be x at pi over 4, and so on. If we wanted to put those subscripts in, that might help us out. Okay, and then the next coordinate point, of course, is here at minus 2, this one. And then the next coordinate point is here, 0 and 2. So we're going this way round. You can see, very good circle. Okay, and we're going this way round in a kind of circle there. And that's the direction of our phase portrait, which we're coming up with. So you can see this is just giving us a circle, and we are trapped in that circle as well. Okay, now, in fact, you can determine the direction pretty straightforwardly by just considering what happens to dx dt when we've got, say, for example, this point here. So dx dt, remember, was 2y. So when we put in this coordinate point here, we can see that if we put in y is equal to 2, when y is equal to 2, there's only one place where y is equal to 2, you can see that we're getting the rate of change of x is 4. Let me say that we are moving in this direction here. And the rate of change here is 4. That's your x dot is equal to 4. Similarly, if you do that for y dot, let's do y dot here, and we'll do that when x is 2. So there we go, when x is 2, we're going to get minus 4. So that's giving us minus 4, and that's going to give us the rate of change of your y value, so how much up and down we're moving at this extreme point here. So we can see that we are moving down at that point. So this is now y dot equals minus 4. And then, of course, if we chose this point, we would get x dot is equal to minus 4. If we chose this point here, we're going to get y dot is equal to plus 4. So that is just telling us our motion around the circle, the way in which we're traveling around this phase portrait over time. And of course, you can see that when you put in this case, when you put in pi, you're going to end up back at the start. Now, this is not talking about this being pi over, this being sort of 2 pi, which it would normally be. We're talking about the movement over time here. So this was actually after pi over 4 in terms of time. We chose a clever point in time there. So we're not talking about the same angles in the unit circle as matching with t. T is this separate parameter, and we've chosen clever values of it. And we can see that when t is equal to pi, that was the clever value which we chose, which is going to say we're going to be back to the start again. So at 0, at pi, at 2 pi, minus pi, at 5 pi, k amounts of pi, we are going to end up back at the start. Okay, so when the point that I'm coming up with over here in terms of the direction, the point in in the note down here at the bottom, it says the direction of the movement can be found by evaluating dy dt for a point on the x-axis or a point on the y-axis. That's exactly what I've done in that question there. That's what all of this was about here, just to find the direction of travel there. Okay, that's our 4. Okay, so that's sorted out with a particular example, and I've chosen obviously a really basic one there, which is giving us a circle. And you can see in the book that they're talking about the fact that you don't always get circles, concentric circles, depending on where you start. You start here and end up with this circle. Start here and you'll end up with a different circle. But sometimes you get ellipses, and sometimes those ellipses are sort of skew. They're not straight on, if you like. So you can get these types of diagrams, but you always end up going round in the same ellipse or in the same circle based on your values of A and B and your eigenvectors. Okay, now we're not being asked to find A and B and those eigenvectors at the moment. Okay, and that's saying that's beyond the course, but I've obviously come up with a concrete example there just to show you one of these. Okay, now beyond this, for parts 2 and onwards, they're talking about the other part of the point. They're talking about spirals and saying, well, let's make this complex number more than just imaginary. Let's take it so that it's got a real part as well, so A as well. Now, this we can deal with fairly quickly, in fact. So you can see that previously we had this and this, and now we're going to change this to say, well, what happens if there's, I don't know, a 1 plus this on the front? What happens if there's an A on the front of this? The complex number is A plus BI and A minus BI as your 2 eigenvalues which are associated here. Now, if you do that, you'll be able to see quite easily, if there was, say, a 1 plus there, you're going to be able to factorize out an e to the t. There would be a 1 plus there, okay? So I'm going to show that in a second just to see that it's quite easy to factorize something out, say, for example, e to the t, and you'll be factorizing out an e to the t there. And that would just be factorizing out right in front of that whole expression. Now, the whole expression we know goes around in, with this factor taken out, we know goes around in circles or ellipses. So if we're timesing by this extra function, e to the t, well, it depends what happens with this extra function. This e to the t might be something else, depending what a is, which we'll show in a second. But that will have the consequence of either making the circle bigger over time or making the circle smaller over time. Okay, so let's just deal with that again. And let's say, if we had instead in here, so this part here, we're saying that that's e to the a plus b I t. Okay, now if we then wrote that in a slightly different way, if we said that's e to the a t plus, not plus, using our laws of indices here, times by e to the b I t, we're going to get, as I said before, you're going to do the same with the other part as well, and you'll be able to factorize this out just with a minus with this other part here. And then overall, we'll be able to take out a factor of e to the at. So what happens with this extra factor? Is this extra factor getting smaller over time, or is it getting larger over time? Well, that's all dependent on what happens with a. If a is greater than 0, then as t tends to infinity, we can see that e to the at is going to tend to infinity as well. Okay, so this is going to get larger and larger. So this is e to a larger and larger positive number. That's obviously going to get really large. Now, if a is less than 0 and t tends to infinity, so say, for example, we had a is -1, then e to the minus t, about e to the minus t, e to the t would be like this, t over time, and this would be t. And e to the minus t would be like this. It's 1 over e to the t. That tends to 0. So we get here e to the at, now think that a is negative, is going to tend to 0. Okay, so that means to say that this circle or spiral is getting larger each time, or it is getting smaller as you go round. So the circle is it's getting smaller, so it's spiraling inwards. So the circle or the ellipse will spiral around either out of control or going towards the source, going towards the origin. Okay, and that's essentially the point which they're making here. Now, I really don't think that it's necessary for you to go and do the rest of the investigation, although of course it's great to have more practice. But 2, 3, 4, and so on just leads to that discovery, essentially, that we're either spiraling outwards if A is positive, and we're spiraling inwards if A is negative. Now, they've dealt with a kind of circle diagram here. Obviously, the bit inside that you're left with once you've factorized out this e to the at could also be giving you an ellipse. So it could be an elliptical thing. So you could be sort of spiraling outwards in an ellipse as well. Again, in order to find the direction in which you're going, so whether you're spiraling one way or the other way, again, there's that extra condition, of course, which they gave to us, which they said you can always check the direction of movement by evaluating y dot or x dot, so dy dt or dx dt on either of the axes. Okay then, guys, so there was a huge long explanation there. Well done if you've got through all of that. You might need to go through a lot of this again really carefully, and it might be useful for you to go through a bit more of the investigation yourself as well. But 12G now is there, so you've got those 2 questions. There's only 2 questions there. And again, we're talking about sketching the phase portraits here for each of these systems down here. So find the eigenvalues to start off with. Okay, let's have a little look at what this is. Some extra stuff here. I'm not sure what this is myself. So we've got exact solutions of coupled differential equations. And they've got some extension questions on this one. So there are more questions which you could get, and these ones are in context. Applications and interpretations. Oh, and they've got some further answers there and some work, a little bit, perhaps a bit of working there as well. So there's some answers to those ones too. Okay, guys, well, good luck with the exercises and hope to see you back for the next one.